Joe, talking about memory forensics for Android.
Thank you. It's a lot less math in this talk than the last one. So just so I know how to gauge the talk, how many people in here are forensics guys, gals? Awesome. Awesome. How many are familiar with operating system internals, Linux kernel internals specifically? All right, sweet. So my name is Joe Sylve. I am a senior security researcher at Digital Forensic Solutions, New Orleans, Louisiana. I have certifications and degrees, all that good stuff. And today we'll talk about Android forensics, specifically Android live forensics. I'll cover what live forensics is, how it usually works in traditional Linux environment, and how it's different with Android. Even though Android is Linux-based, we can't use our traditional methods necessarily. And then we will discuss and demo some new tools we make to get the job done. So first of all, what is live forensics? In traditional forensics, I don't want to call it dead forensics because that leads to more CSI stuff, but traditional forensics, you're usually doing things offline. You're studying non-volatile data, hard drives, flash drives, CD drives. You're doing it in your own environment, on your own time. Live forensics, you're running it on a live machine. You're doing it mostly on RAM dumps, but as most of us know, if you shut off a computer or you reset a computer, you lose all the contents in RAM. So a caveat to that is it must be collected on running machine, which means if you're investigating an attacker's machine, you're investigating it on his terms, not on our terms, not in a secure lab environment. If there are any tools running that can detect this stuff, you can just reset the device and you lose all the information you're trying to get. But live forensics is useful. RAM dumps provide a whole lot of information. Basically anything that's ever read or written to a computer has got to go through RAM at some point in time. And a lot of it's not cleared. So just even running a simple strings on a RAM dump, you're going to get conversations on a phone, you're going to get text messages and emails, you're going to get passwords, you're going to get all kinds of neat stuff, and that stuff's very important, obviously. You also get things with full RAM dumps, kernel and application structure, so you can even rebuild the state of the computer, get running processes, see what files are open, see what network connections are open, and you even get historical data. You'll get processes that were open maybe an hour ago, a month ago, depending on how active the machine is. So this stuff is pretty useful. More specifically, advanced malware. A lot of malware is coming out now where it's not ever writing anything to the hard drive in an unencrypted fashion, or not writing anything to the hard drive at all. It's just completely RAM resident. So without live forensics, you would not be able to analyze this stuff as easily. And encrypted or temporary file systems, those are never written to the hard drive in an unencrypted fashion. So even if you have encrypted file system mounted, you can usually get a copy of that if the machine's running. But if it's not, and it was unmounted, you can still sometimes fetch the keys. Temp file systems, that's their own thing, and they're all, majority of them in RAM most of the time. And in the past few years, they have some analysis tools come out for live forensics, FATKit, memparser, and we'll talk about volatility, some really cool tools. So Android, out of the smartphone market, 43% of those phones are Android phones. And these are old statistics. This is Q3 2011. It's way higher now. I read something recently that said Android is more than 50% of the smartphone market worldwide. And we're not just talking phones. We're talking TVs. They're Android TVs. They're Android-powered tablets. They're Android computers. And then there's a bunch of stuff that's like between a computer and a tablet or between a phone and a tablet. There are tons of devices, and they're everywhere, which means they're connected to your network. They're accessing your data, and they're getting owned. So it's very important that we are able to do forensic analysis on this just as much as we want to do a laptop or a server, even more so, because I don't know about the rest of you, but the majority of my life is in my phone. So it's a lot of data. So the first step of this is acquisition. We need to be able to get the dump of RAM before we can do anything with it. Traditionally, on Linux devices, you could do this through a number of ways, either through hardware or software. JTAG usually gives us an interface where we can debug the hardware directly, sort of freeze everything, read the copies of RAM. Interfaces like Firewire and Thunderbolt, they're direct memory access. The reason they're so fast is they can directly address RAM and read from write from RAM without going through the operating system. So there's a lot of really cool research where you plug in a device into a Firewire or a Thunderbolt port, and you get a dump of RAM. Doesn't matter if the computer's logged in, the computer just needs to be on. And can of compressed air, the cold boot attacks that came out a couple years ago, those are really neat. Take a can of compressed air, you turn it upside down, you spray down the RAM chip, it gets really, really cold, and even when the device loses power, it doesn't lose the data from the RAM, sometimes for up to 10 minutes, depending on how cold you get the chip. So you can pull the RAM chip out, pop it in another box that you know is not going to wipe RAM when you start it up, boot into a minimal Linux environment, and copy your image of RAM. This is how I think they first got past BitLocker and got the keys. And their software, traditionally Linux systems used to have dev mem and dev kmem devices that allowed you to read and write from memory from user LAN, albeit with restrictions. That's sort of phased out in the past few years. So there are others that come out, FMEM and Crash are two of the notable ones. And those still work on desktop systems and servers very well, but for reasons that we'll get into later, they're not going to work on our Android devices. And then there's some other research where you can use ptrace or cause a process to core dump. And that way, it dumps its entire core, you get the contents of its RAM, but it's just process specific. These do work on Android, but we're only getting one process, and optimally, we want to get everything. So, what doesn't work on Android? JTAG may work. Many devices still have JTAG ports, but good luck taking that device apart, getting to the JTAG port without removing the battery. And then it's going to be different on every device. So while possible, it's not really a reasonable method of attack for us for these devices. Most Android devices aren't going to have any DMA hardware. So you're not going to have Firewire, you're not going to have Thunderbolt, so that's out the window. Unless you wanted to freeze the entire phone, can of compressed air probably won't help us here. And even once it's frozen, we have no way of getting those RAM chips out because they're soldered onto the main board. So, yes?
What about HDMI ports?
I was thinking about that earlier. I don't think that HDMI is direct memory access. I may be wrong about that, but it could be an avenue. But not all phones obviously have HDMI ports either. Software side. Most Android phones are no longer shipping with dev mem or dev kmem, and if they are, they're very limited. You can only read the first 896 megs of RAM, and there are limitations. And for reasons that I'll get into specifically next, FMEM and Crash, unfortunately, even when you cross-compile them, won't work for Android. Now, as I mentioned earlier, you can still get process-specific dumps, but there's a lot more information, and you're limited with process-specific dumps to processes that are currently running. And we don't necessarily just need information on processes that are currently running. We want to get into the kernel data. We want to get encryption keys. We want to get all the cool stuff. And we're not going to be able to get information about a process that just exited if it's with these techniques. So, going to why FMEM and Crash is very similar. Crash is just made by Red Hat, how it works, and then why it won't work on Android. So basically it starts by you use DD. FMEM is a loadable kernel module, and when you load it, it gives you a virtual device that you can read from user LAN. You use DD, in file to dev FMEM. It gets a starting offset specified by the read operation. It goes and it looks to see if that starting offset is RAM or not. And I'll get into that a little bit specifically in a second. And if it is, it'll do the physical to virtual page translation, copy out the contents of RAM, and dump it over. And then for the next block, it'll do the same thing, and next block, it'll do the same thing. First reason it won't work is step one won't work for us. Physical RAM is not always mapped linearly. It has gaps, and it's not always mapped at 0. So when you're trying to read from a logical virtual address of 0, it's not necessarily going to translate to a physical RAM address of 0. You're going to have all kinds of different physical addressing. If you see the two here that say system RAM, those are the ones that actually map to our RAM chips. So logical address 0 might actually be physical address 20000, and this is going to be different on many different devices. So we need to be able to tell when we're going through with DD and you're sweeping this range of physical addresses, you need to be able to tell which one of these are RAM and which one of these addresses are mapped to a different hardware device or a virtual device. Because if you read or write to an address that's not RAM, you get all kinds of weird stuff happening. And usually it means a kernel panic, the phone reboots, and we just lost all the data that we're trying to collect. Because when the phone reboots, volatile data is gone, and every system that we've tested. So generally when you're using DD, using FMEM, you're using DD. And Android does ship with a version of DD out of the box, which is good. But if our addresses of system RAM are located low enough in the physical address range, if they're at 0, even 2000, that might be okay. But if for whatever reason, we've seen several devices that work like this, system RAM could be mapped anywhere. So if it's arbitrarily mapped at a high address range, it won't work, and this is why. So you're passing it skip either implicitly or not. When you're going to dev mem, it'll start at 0 and go all the way through. But eventually, to the kernel module, it looks the same. So it's going to get an address where it's saying, for this block, I want you to seek to this address to read from it. And if our address, fmem calls the kernel function lseek, which takes an offset, which is a 32-bit integer. Lseek calls a function called VFS LLSeek inside the kernel, which takes a 64-bit integer. So that means if we're passing original offset, it's something like hex 800, a bunch of zeros, and it gets translated from a 32-bit integer to a 64-bit integer, since that 8 in binary starts with a 1, when it gets signed extended, instead of getting a bunch of zeros and 8 and a bunch of zeros, we're going to get a bunch of Fs and 8 and a bunch of zeros because it's just going to sign extend it and fill all the areas with 1s. And now what we have is a really high address range that's not valid. So first of all, this is not FMEM's fault. This is an implementation problem and a stripped-down version of DD that Android ships with. However, even if we put a different version of DD that didn't have this problem, that called LLSeek or what have you, it's still suboptimal, because for every block that we're reading from physical memory, we're having to make a call from user space to kernel space. And every time, that means a context switch, and that means we're perturbing memory. And what we need to realize is doing live forensics is like Schrodinger's forensics. When you're in the system, when you're getting information from the system, you're modifying the system, and we need to try to minimize that as much as possible. So there's a better way. The second reason FMEM won't work out of the box, even without the DD dependency, is the second part, where it has to correlate a physical address to decide whether or not it's RAM. FMEM does it by calling a function called pages RAM in the Linux kernel, which basically goes through all the pages and checks the flags and sees, okay, going through the data structure, is this mapped to RAM or is this mapped to a hardware device? Unfortunately, this function doesn't exist in the ARM version of the Linux kernel. So we can't compile it. We can modify it and do this own functionality by our own, but still suboptimal because of the reasons specified earlier. So instead of, we first started out to modify FMEM, and when it came clear that it was basically going to go up to a rewrite, we decided to approach it in a different way. So we created DMD. Something I wrote. This currently stands for Droid Memory Dumper, but it needs a better name, and we'll get into that soon. You'll see why. It's also a loadable kernel module like fmem, but instead you don't have to use any userland programs to interact with it except for insmod, which is installing the kernel module. You can dump memory either directly to the file system on the phone, which would usually be your SD card, or over the network. And you don't necessarily have to connect the device through your network. You can do it through the Android debug bridge over USB. And the goal for DMD is to minimize this interaction between userland and kernel land. We want to handle all the lookups in kernel. We want to know which addresses we have to read from, and we want to just do all the writing from kernel land. That way we're not perturbing memory as we go. So, very simple how it works. We try to keep it as simple as possible. In the Linux kernel, there's a data structure, and it's named IOMem resource. And that data structure, basically, when you go through the proc IOMem, it's just parsing that data structure. This is the information it has. It's got the addresses of physical RAM addressing and corresponding information to what it goes to. So rather than seeking through all the known address space and trying to determine whether that address space is RAM or not, we just simply go through that resource and look for the system RAM, and then we copy out that. And we can write it to the SD card, or we can send it over to the network. This is designed to do one thing, and it does one thing, and does pretty well. And it does it all in kernel land, so that means less context switching, which means faster. And when you're doing a RAM dump, speed matters, because the longer you're running something on a running system, still has processes running, it's going to modify things, and we want to try to minimize that. And it's pretty portable. So it goes through there, and it does the same thing as fmem, basically steps 3 and 4. It does the physical or virtual address, and then it writes it all, but all from the kernel. So an example of how it works, pretty simple. This is an example of how to do it over the network. Use the Android debug bridge, which just ships with the Android developer kit. ADB push, the first command just copies our kernel module over to the device, writes it to the SD card. The second command, ADB forward, TCP, blah, 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 forwards a port from the device to the host. So if I map port 1234 on my phone to port 1234 on my laptop, anytime I connect to the socket on connect the socket to the port on my laptop, it maps the same port on the phone. So this allows us to do networking without actually having to connect the device to our network. And then ADB shell, we get a shell on the phone. SU obviously gives us root. It is important to know that to install a kernel module, you do need root. And this is the same caveat that we have if we're doing it on a desktop or a server system. So it is important to have, if the phone's not rooted already, a good forensic investigator is going to have a toolkit of not only root exploits, but root exploits that you don't need to reboot the phone with, which, I mean, it's just what we have to deal with, but it's what we have to deal with in live forensics on desktop systems anyway. So we call insmod, which installs the kernel module, and it has one parameter, path. And path can either be a folder, a directory on the device itself, in which case it will automatically go through and read all the memory contents and write it to a directory on the SD card, or TCP and a port number. If you give it a port number, it'll open up, it'll listen to a port, it'll wait for connection. As soon as it gets connection, it'll start reading through RAM, and it'll just push it all over that socket. So then on our host, we do a netcat connection to localhost at the port that we map, and we just pipe the output to a dump. Very simple. If we want to do it over an SD card, it's even simpler. Just everything keeps maintained on the device itself. We do insmod, and path is just SD card, and we don't have the forwarding ports in this example. So, for you forensic investigators in here, I understand, so please don't anger the moose. We are violating the order of volatility here. Generally, if you can, you want to try to collect the most volatile information first before you connect the stuff that's going to last longer. Because we have to get our tools onto the device, we don't have a USB port that's got host drivers necessarily that we can just plug a drive in and have our tools. So we need to copy our tools to the device. That basically gives us 3 places to copy it. We can copy it on the SD card, we can copy it on the NAND flash of the device, or we can copy into a temp file system, but that would just copy it in a RAM, and we don't want to stick our tool in a RAM that we're just about to copy, because it's already going to go in there a little bit when it's running, so we want to try to minimize the interaction we're having with the operating system. You cannot simply just put in a fresh SD card in a lot of these devices because the SD cards are located under the battery. So if you take the battery out, even if it's plugged into the wall, it dies. We wipe everything. So solution, what you have to do is sort of violate the order of volatility, mount the SD card through the phone, which you can do, it's a simple setting, to the host, image the SD card, remount the SD card, and then do the RAM capture. It's not optimal, but it's what we have to do to get our tools on the device, and it's just another downside about live forensics. All right, so I'm going to demo the first part, and we all know how these things work, so do what you need to do. All right, so what we have here is the Android emulator. And the good thing about the Android emulator is it emulates the hardware more than the software. So it's actually running the full stack all the way down to the kernel. So we can test kernel modules, we can test a bunch of things on the emulator because it's QEMU, and before we try it on a device. So we have our emulator running. I am going to push to the SD card of the device. I'm going to forward my port. And again, this is just mapping a port 1, 2, 3, 4, 5 from the device to my laptop. I'm going to shell. And I'm already root, which is great. All right, so now DMD has opened up a socket bound and is listening for a connection. So let's give it a connection. And I'm just going to pipe it through PV, so you don't have to do that. It's just so that we can see some progress as it's going. So this is just netcat to a port, local port on the computer, which will go through the Android debug bridge and connect to a port on the Android device, and pass it through the pipe viewer, and then just dump it to the file system. So, all right. That's going to take a minute or so, so we'll move on. All right, so this works. We've tested it on the emulator. We've tested it on a myriad of devices. It works, but we needed to know how well did it work. And what we get is a chicken and the egg problem, because to decide how well it works, you need a snapshot of RAM to compare a snapshot of RAM that your tool get, and how are you going to get that, first of all? Well, this is where the emulator helps us again. The emulator has the functionality to be able to basically freeze its state and just give us a snapshot of RAM at any given point in time. So that's great. Now we have our ground truth. And then we do that. We get our ground truth, and then we immediately run DMD to get an image, and then we just compare the two images. And we do it page by page and count up how many of these pages are identical and how many of them have been changed. And what we found was the DMD works. It's 99.x% effective in almost every case we've done it. When we did this 10, 50 times. So great. When we wanted to compare it against the other tools, so what we did was we modified FMEM slightly to get over the problem that it had with deciding whether page was RAM, so that we could just give it a specific address range. And luckily, the Android OS maps physical RAM starting at address 0, so we didn't have the problems with DD. And so we just repeated the experiment with FMEM. And we found that that was 80% effective. And our hypothesis there is it's because of all the context switching. It's because every block that you're reading from DD, you're doing all this context switching, and it's messing with RAM. It takes longer. So we really think that our method of just doing all of this in RAM is a good thing. And the good thing about that is it's portable. It doesn't just work on Android. It works on all Linux devices, or it should. So that's why DMD needs a better name. All right, so now that we have a RAM capture, what do we do with it? Well, that's when we turn to the Volatility project. For those of you who are not familiar with Volatility, it's a really cool project. It started out as RAM analysis strictly for Windows, but my co-researcher, Andrew Case, one of his contributions was he worked on the Linux port. So it actually now works with Linux dumps as well. And so I came to Andrew and I was like, you're working on this Linux thing, I'm working on this thing to dump RAM. Let's figure it out and let's get Volatility working with these RAM dumps. So now, or in a couple of weeks when we release, Volatility actually work with ARM devices as well, ARM Linux devices, including Android. So the goal of Volatility is you want to have a tool set to where you can take a RAM dump and parse through the kernel instructions and get all kinds of information you would as if you were investigating a machine. On a machine, if I want to know what processes I'm running, I type PS and I get a list of processes. In Volatility, you can do a very similar thing. You just get a list of the processes. Or you can get a list of memory maps. You get command line arguments from those processes that are retrieved from userland. Kavit, star, there's a bug right now. This doesn't work for ARM, but it will as soon as we figure out that problem. You can get memory maps of limit the processes, and the cool thing about that is, okay, so you have an unknown binary running. You see it in the RAM dump. It's not on disk. You don't know what it is. You can actually pull that binary from memory, from the RAM dump, using Volatility, and analyze it with, reverse engineer it with IDA or whatever, what have you. Asterisk on that one too. It only works sometimes because it's the same thing. There's a bug with mapping userland memory. You can get open files of a process and sockets. A bunch of networking information. You can get, basically the same information you get if you hit ifconfig, the gateway and all that good stuff. Open sockets with netstat, ARP tables, routing cache, all kinds of cool stuff. You can get kernel debug buffer, just as if you would be typing dmessage. You can find all the loaded kernel modules, which would be very useful because most Linux rootkits are kernel modules. And see a list of file systems, a bunch of cool stuff. The very cool thing is, since this is RAM, and RAM's not always cleared, you're not only getting processes that are running when you do the dump. You might be getting processes that have already executed. The kernel keeps a structure called a QueMemcache, which it handles its allocation from. And it has a free list. And so if we just simply walk that free list for information that the kernel says, I'm done with, this is no longer interesting, well, it might not be interesting for the kernel, but it's still interesting for us as forensic researchers. So we can get information about processes that have already exited or old network connections or what have you. You can get processes, memory maps, network information. So it has a few limitations. It really depends on how aggressive the allocator is. Your SLUB, SLAB, SL, QB, they're all different, and they all handle process deallocation a little bit differently, and some of them wipe these free tables more quickly than the other. And if a process is nulling all of it, writing null to all of its references before it's deallocating itself, well, we no longer have those references to follow, even if we have the data structures. But it seems to be pretty effective. So other cool stuff you can do with Volatility. Andrew actually gave a talk at the Open Memory Forensics Workshop last year that discussed all the thing, and his presentation slides are at that link. Some rootkit detection. He did a presentation at Black Hat where he uses these methods to take a live CD, and someone's booting into a live CD, backtrack CD or what have you. They're doing their thing, nothing's being written to disk. If you get a dump of that session while the computer's still on, you can use Volatility to go through that and rebuild file system and cool stuff like that. And soon, Dalvik analysis. For those of you who don't know, Dalvik is like the runtime engine of Android. So even the current functionality will go through native applications. We're going to have some Dalvik-specific stuff. So you want to go through the Gmail app and figure out, who was the list of last people contacted or stuff like that. We can automate that. It'll be cool. But that's not out yet. All right, so hopefully if the first demo worked, we can go to the second demo. All right, excellent. So it looks like we have our Goldfish demo, 256 megs. That's exactly what it should be. All right. So let's demonstrate some of this volatility stuff. So what we have here is we have a profile called Goldfish, and that's a volatility profile I made specifically for the kernel that's running on the Android device. And it's really simple. It's just a few steps. You can do it with any type of kernel, and it just generates a file that gives volatility all the information to know what's where in the kernel, so it can find all the information it needs. So we pass it Goldfish, and then we type F and pass it the RAM dump. And if you look here at info, there's all kinds of options that we could be passing it. Specifically, all these that say Linux are the ones that we're interested in. So some cool stuff we can do with those. Linux. Here's a list of all the running processes and their process IDs and the user IDs that we're running from. That's cool. You can see, you notice INSMod was running when the device was capturing memory, because obviously that shows that we installed our module to capture the memory. And the shell, SH, is going to be the shell that we were running as well. You want the... Here's the kernel debug messages, just as if you would have typed DMASG on the device. You want networking, we can give you networking. Netstat would give you just the same as if you type netstat, although there are probably no network connections. Yeah, there were no network connections connected to the emulator at the time. Let's see if we wanted the process maps, specific process. 293 would be the shell. So here are the process maps. We're showing the different address ranges for the memory regions of that userland process. And if there wasn't for the bug, we could actually pull that binary out of RAM with another command. Routing tables. Cool stuff. So yeah, there are a myriad of plugins, and most of the ones that work on Linux will work on ARM, and by the time we release, they all will. So I'm good. It worked. All right. So DMD, Droid Memory Dumper. One, it's kind of a lame name. It's kind of generic. We need a better name. And it works on Linux, so it's not just a Droid thing. So we are taking suggestions. So I was going to set up a system so people could vote on it, but we're on a con network, and I don't trust them. So you send me an email, shoot me a tweet, and the best name, I'll mail you a homebrew, or if you come down to New Orleans for Mardi Gras, I'll buy you more than that. It'll be fun. So a little bit about our company. We're Digital Forensic Solutions. We do computer security, research, penetration testing, all that good stuff. But some other products that they're all free that you may have already heard of. Registry Decoder, it's sort of a Windows registry triage tool that doesn't suck. Scalpel is a file carver, and DMD. DMD is going to come out, probably I'll release it next week under the new name that one of you give me. And So keep track of our blog. We'll announce when we release that, and it's going to be all open source. So if you have any questions, you can ask me. My CEO, Daryl's running around here. She's got a hat with a flower on it. There's a paper that we recently published that basically covers everything that I talked in this talk in more detail, called Acquisition of Analysis of Volatile Memory from Android Devices, and that's in Digital Investigation. There's a copy of it at that link there. So read through the paper if you're at all interested in this sort of thing. And, of course, there's Digital Forensic Solutions. So any questions? I went through that quicker than I thought. Yes, sir.
In the case where you use the modified FMEM tool and it stopped on 20% of the memory, did you do any before and after analysis to see what was in that 20%? Because unless I'm mistaken, would that just be unallocated memory that was previously allocated to the running process?
Well, what we did was we used the same testing process as we did with DMD. So, okay, I'm sorry. The question was, he asked about, I'm going to find it. He asked about the testing we did with this and when we modified FMEM. And correct me if I misquote your question, but he wanted to know if we did any like before and after testing to see what exactly changed.
Well, exactly was in the memory that got stopped on. It wasn't interesting.
Okay, so there's a misunderstanding. The 80% there is not that it only recovered 80% of the address range. We got, for a 256 megabyte device, we got 256 megabytes. But 80% of the pages had changed from our base truth. So what we did first is we took a snapshot of RAM through the emulator, and then we took a snapshot of RAM through FMEM, and then we compared those two snapshots and said, okay, is the first page, is that the same? Is the second page, is that the same? And went through. And only 80% of the pages were identical to our ground truth. So this is just sort of a method of us saying, not can we explore the entire address range, but how valid is our image?
Okay, but in those cases, those pages that were different, before they were stopped on by FMEM, was that zeros? Was it interesting data? Was it important?
We didn't dig into it too deeply. Generally, it's going to be data from running processes, I would imagine, but I know more research needed. And I'd gladly do a follow-up if it's requested. Any other questions? I think maybe ahead of my time. I don't want to dance for 10 minutes. I can't see there's a light. So whoever has a question, just go ahead and ask it.
So in order to run your tool, you need to be rooted. Is that correct?
That is correct.
So on these numbers, were you assuming that the device that you're analyzing was already rooted, or does that 99% include the rooting process?
Yeah, this is because the only way we could get ground truth is by using the emulator. I'm sorry, the question was, since the device needs to be rooted, were these numbers before root or after root? Does it take into account the rooting process? And the answer is because we had to use the emulator for this to be able to get ground truth in the first place, the emulator is already rooted. So these numbers are not including the root. And now you're going to have to use a different rooting method for several different devices. So those numbers would definitely change based on how you were rooting it. But that would be independent of the collection method. So if pages were changed because you had to root the device, that would be the same between DMD and FMEM because the tool itself is not actually doing the rooting. Yes?
So when you did NetStat, there were no network connections. When you did NetStat, it showed no network connections, but it used TCP port connections.
All right, I heard the first part of the question where you said when you did NetStat, it showed no connections, and I'm sorry, I couldn't hear you after that. Correct. That is a good point. He said that we did open a TCP connection to dump the memory, and it did not show on the NetStat. We need to make sure that's not a bug. Thank you. I didn't consider that. Okay, well, if there are no more general questions, I'm going to get off the stage. I'll be around. Daryl will be around. So if you have any questions, let me know. Thank you.